Chapter 3, Describing Data Using Numerical Measures. So make sure to follow along using the Chapter 3 Practice Problems worksheet. In this video, we'll discuss the range, interquartile range, variance, and standard deviation, and what these values mean. So recall in the previous video, we discussed measures of center and location. In this video, we'll discuss the measures of dispersion and variation. So when we're describing data, we're actually looking for the spread. When we collect data, we'll notice that the values for our variable of interest will take on different values. And when we plot them, it spreads around the center. So we want to see how far the spread occurs. Variation occurs in everything that we do. Not everything's going to fall with the exact same number. It's going to vary depending on a variety of factors. And so when we're measuring variation, it's giving us the information about our spread or how different they are from each other. If there's a smaller value, there's less variation. If there are larger values, there's more variation. So we can see here in the diagram that while our two shapes here have the same center or midpoint, they have different variation. The taller one is more tight in that the different values are much closer together, whereas our wider curve here has greater variation, meaning that the numbers are spread out farther from each other. Or one measure that you might want to calculate is the range. To calculate the range, we take our largest value and we subtract it from our smallest value. It's the easiest form of measurement. It is very sensitive to extreme values though. So if you have a very large number and a very small number, but the majority of your data is somewhere in the middle, this range will skew that. It also ignores how the data is distributed. Another type of range that we might want to calculate is interquartile range. So recall you learned how to calculate the first and third quartiles. So to get the interquartile range, we're just getting the difference between the first and third quartiles. So recall the box and whisker plots, where, for instance, if our first quartile is 30 here, and our third quartile is 57, we just subtract the two, and that will give us our distance or our range. So there is an interquartile range of 27. Again, what this does is it focuses on the data that's towards our center and will ignore the more extreme numbers. Another form of variation that we're going to often use throughout the semester, so it's really important that we get a good understanding of it, is population variance. So this is the average of the squared distances of the data values from the mean. So here we have our formula using our various Greek letters. So let's make sure we understand what each symbol means. Here is our mu, that's our population mean, and we learned how to do that previously. Our big N, that's our total population size. And this symbol here is sigma squared, which means population variance. So what you'll be doing is, following our order of operations, we will take each value that we're working with and subtract the mean from it and then squaring it. So we're squaring the distances between our particular data value and the average. After we square each one, we add them all up. Then we'll take that sum and divide it by our total population size. There's also a shortcut formula here, but I generally don't use it. I prefer this formula right here. Based on the population variance, we can then find our population standard deviation. This is the most commonly used measure of variation. And all we do is we square root the variance. So you can see here, this is the same formula for our population variance. And here's the symbol for population variance, and we will square root it. And so when you see sigma by itself, that means population standard deviation. Let's go ahead and practice. This is problem 26 from the textbook. It's also on your worksheet. We have data here that reflects the number of times a population of business executives flew on a business last month. So remember, the population is the frame that you create. So let's say we are looking at a particular company and their population of business execs, they only have 6. So here are the number of times those 6 executives flew on business last month. The first thing we're asked to do here in this problem is to compute the range. So recall we're going to take our largest number and subtract it by our smallest number. So we'll take 9 minus 4, and that gives us a range of 5. The next step is we want to calculate the variance and standard deviation. Before we can do that, we first want to find our population mean. So here's the formula to calculate the population mean. In other words, I'm going to add up my 6 numbers here for my numerator, and I'll divide it by my total population size, in this case 6. So 35 is the sum of all the business flights last month, and we had 6 executives flying. So our population mean will be 5.8333. As a rule of thumb, and you'll often see in my stat lab, it will ask you to round to the 4th place. Now, what I suggest is using a table to help organize our calculations when working with variance and standard deviation. And so the first thing we want to do is figure out what is our big N. And again, we've got 6 data points here. So we know our population size is 6. Now the next task, according to our table, is I'm going to take my variable, or my x, in this case 4, and I'm going to subtract my population mean, which we solved for on the previous slide. So here I'm going to take my 4 minus 5.8333, and that gives me a negative 1.8333. And I will repeat this for each value that I have. So this is the distance between my x value and the average of all my values together. The next column here in our table tells us that we'll take the difference we found in our second column and square it. So recall that the definition of a population variance is the squared distances. So here I'll take my negative 1.8333 and square it. And that will give me 3.3611. So I'll continue down the table, and I'm going to square each of my distances to get my squared distances. According to our formula, to find the variance, we want to add up all of our squared distances. So go ahead and add up everything in this third column right here, and that will give us 18.8333. Now I can go ahead and plug in my values into the formula. So again, we just added up all of our squared distances. So there's my 18.8333. And then I'm going to divide it by my big N. That's 6. And then my variance will be 3.1389. To find my standard deviation, I'm going to square root my variance. So I'll bring my 3.1389 down here under my square root symbol and plug that into my calculator to determine that my population standard deviation is 1.7717. And that's how you can calculate the variance and standard deviation by hand using a table. I use the table because it helps me organize my calculations as opposed to doing it all into a calculator where I might accidentally make an error and I can't find where my error occurred. By doing it this way, I can always review it and see perhaps I did a typo or wrote something down wrong or added something incorrectly. Now, if you were asked to compute a sample standard deviation, again, this is sample data that is pulled from the population. We have these formulas here. So whereas our variance and standard deviation had our Greek symbol of sigma, here we're going to use the lowercase s to let you know that we're doing sample variance and sample standard deviation. So s squared is our sample variance. And here what our formula is telling us is that I'm going to take my x, or my value or variable that I have, and I'm going to subtract the sample mean. Recall x bar means my sample mean. So again, this tells us I'm working with my sample. So it's the same process of where I'm taking my value and I'm subtracting it from the mean and squaring it to get the squared distances. And then I will add them all up. Note in the denominator though, now I'm working with my sample size, little n, and subtract 1. So that's the formula for sample variance. And then to get your sample standard deviation, you will square root whatever you found in the variance. Our step 1 is to pull our sample and record our data. Step 2 just reminds us to use the correct formula to calculate a sample variance, which you saw in the last slide. Our next step is to calculate the average, or our sample mean, and then we will find the sum of square deviations for each x value from our sample mean. That's where we subtract our value from our sample mean and then square it. Then we'll calculate our variance, and from there square root it to get the standard deviation. I find it easier if we just walk through the process. So let's continue. It's the same problem, same data set, but we're now going to find the sample standard deviation. So recall you already in the table on your worksheet in the previous slides, we've already found our values, subtract the mean, and squared it. So that was the 18.8333 that we calculated earlier. Because it is a sample variance though, our denominator is sample size n minus 1. So recall our sample size was 6, and so we'll do 6 minus 1. In other words, 18.8333 divided by 5 will give us a sample variance of 3.7667. To get the sample standard deviation, I'm just going to take my variance, plug it under my square root symbol, and so my sample standard deviation is 1.9408. Now if you look at the answers you got in part B and part C and compared the two, you'll notice that our statistics from the sample will be larger than our parameters that we calculated for the population, because the division for S and S2 uses a divisor of n minus 1 instead of big N. So when we compare standard deviations, you can see here in our example, we have data points here where the mean is the same. They all have the same mean of 15.5. But depending where our data points fall, and once we subtract and square the distance between our data points from this mean and divide by the appropriate denominator, in this case with a sample we're dividing by the sample size minus 1, we get different standard deviations. Here our standard deviation is 3.338, so it's spread out widely. And then here you can see our dots are close towards the mean. That means our standard deviation is small at 0.9258. And then here in data C, even though I've got some points close together in different areas, because they are far apart in relation to each other and to the mean, we see that our sample standard deviation is even larger than that of data A at 4.57. So it's helpful to imagine where your data points fall within the number line so that you can see how far your spread is or your variation. And is it tight or is it wide? And so our standard deviations will let us know how far away we are from the mean.